So far, we have everything we studied so far: linear, quadratic, cubic, reciprocal function, deal with additive growth or some kind of fixed rate of changes. But in the real world, sometimes there's multiplication of changes, not just addition. For example, let's say you think about population growth. You might not just add the same number of people each year. Potentially, every new person can have more children, which can have more children and have more children. So there's kind of multiplication growth going here. And for example, if you save a lot of money in your bank, right, there's compound interest. You don't just earn interest on your original deposit, you also earn interest on your interest. So the more money you have, the more interest you have, which gives you the more money to even earn interest. We call this exponential growth. And the best way to learn about this is to start with an example. Here's a question about bacterial growth. Read through the question and then try to do it on yourself. In this question, we have a new type of bacteria that is placed in the petri dish in the science lab. At first, there is one bacterium. Every hour, the bacteria double in number. We are supposed to write down an equation for the number of bacteria n after x hours and complete the table for x equal to 0, 1, 2, 3, 4, and 5. And then we have to plot the graph of of n versus x. And we have to estimate the number of bacteria after 4.5 hours. The equation is n equal to 2 to the power x. This is because the bacteria double in number every hour. So x is number of hours. So when x equal to 0, there's only one bacteria, as 2 to the power 0 equal to 1. And then as x increase, the bacteria double in number. So let's draw a table with x equal to 0, 1, 2, 3, 4, 5. As I mentioned, when x equal to 0, n equal to 1. When x equal to 1, n equal to 2. And when x equal to 2, n equal to 4. And then it double from there. So 1, 2, 4, 8, 16, 32. After this, we should plot a curve through the points. And then using the curve, let's try to estimate the number of bacteria after 4.5 hours. From the graph, you can see that at x equal to 4.5, n is roughly about 22. The number of bacteria after 4.5 hours is 22. Why exponential graph is useful is because there are many things in the world that follow this pattern of exponential growth. As what we learned, bacterial growth is one of this pattern. One bacterium can become 2, 2 become 4, 4 become 8. Each generation doubles the previous generation. This creates an explosive growth that polynomial function cannot model. Exponential function can also model decay. When radioactive materials decay, it doesn't lose a fixed amount every day. It loses a fixed percentage. Half-life exactly, actually. It means that half of whatever remains disappear in a fixed time period. Whether you start with 1 million atoms or 100, half will be gone in the same period. The comparison is important. Cubic function grows steadily. Reciprocal function shows some inverse relationship with asymptotes. But exponential function show multiplication-based changes. This is the fastest possible growth and the most realistic decay patterns. This is why exponential functions are essential for modeling, finance, population dynamics, technology, and other real-world phenomena.
Smash your maths exams. Download Learn Maths Today for real exam questions and achieve top marks.